So, 23 people surveyed. So, when you look at this, it says read the labels on the rows and columns of the two-way table. Make sure you understand the labels. So, when you look up here, okay, when you see something like this or some chips or pretzels, we call these categorical variables. Okay, think of the word category. Okay, so these are.
Bless you. Bless you.
They are not numbers, so they cannot be graphed. But they can be put into a two-way table or a frequency table. So that's what a categorical variable is. So just think of the word category. You can't really graph a category because it's just that. It's category. Okay. Now, labels like age is less than 30 or things like that, we call these numerical values. And we'll explain kind of what a numerical value is in just a second. You'll see it on the next example. But obviously, these are numbers that can be graphed. Okay. So categorical and numerical variables. Okay. All right, so if you look at the table, we're going to put tally marks in the cells of the table. So if you look at the table, I want to know, look at the table, count them up. The number of people who prefer chips that are under the age of 30, so 29 or less. How many people is that? Count them up. The number of people who prefer chips that are basically under 30, 29 or less. Jacob. 9, right? Now if we write tally marks for 9, 2, 3, 4, 5, and the line goes through for 5. Okay, right? That's 9 in tally marks, right? Little tick marks. How many people, same age, but prefer pretzels? Less than 30 that prefer pretzels. How many people is that? Shane?
4.
4. So then we're just going to put 4 little tick marks because we don't need to put a line to that. That's less than 5. All right, what about the old folks, my people? Prefer chips that are greater than or equal to 30. 3, right? And then what about prefer pretzels? How many people prefer pretzels? 7. Okay. So the data that we have in here, we call this raw data. Because it's just the numerical results. Okay, raw data. So it says based on the raw data, does it seem like 3 times as many young people prefer chips, so this number, than older people? Just looking at that. It's 3 times as many young people than older people prefer chips. Would you say yes or no? Yes, why? Don't look that deep into it. Why would you say that? Why would it be 3 times more? Right, 3 times 3 is 9, right? 9 is 3 times more than 3. So, yeah, just by looking at that. Right? Now, watch. Now we're going to try to include a totals column. Okay? So, we said already that this was 9, this was 3, this was 4, and that was 7. So, how many total people were there that were under the age of 30? Total people. Peter? 13, right? 9 plus 4, and across, right? If you count that table on the left up top, you count 13 of them, right? How many people are there 30 or older? 10, right? How many total people were there in this thing? 23, right? You can add this up, that's 23, right? So if I were to go in this direction, it adds up to 23. All right, how many total people, forget the age, prefer chips? How many total people prefer chips? 12. Because we're adding this way now. And how many total people prefer pretzels? And now, if you notice, if I add this way, I also get 23. Okay? Now, think about this. Okay? Does the information change for the number of people who prefer chips than older people? Well, there's 9 people who prefer chips, right? Or less than 30 out of 13. Okay? So think about this for a minute. So 9 out of 13. And for the older people, because there's less of the older people that were surveyed, right? That was 3 out of 10. Well, are these two fractions the same? No. So let's try to make this, let's get a common denominator. If we took 13 and 10 and multiplied them together, what would I get? 130, right? So if I multiply this by 10 each numerator and denominator, I get 90 over 130. And then for this one, I have to multiply them by 13 to get a common denominator. And I get 39. So I got 90 over 130 and 39 over 130. So remember, this fraction right here is for the older people, 30 or older, and this is for the people under 30. Is that 3 times more? The 90 over 30, 130, is that 3 times more than the 39 over 130? No, because what's 3 times 39? Is it 90? No, it's like 117. So this will be under, now, because we looked at it a little differently, this is false. Because 39 times 3 is 117. And 117 doesn't equal 90. So it's not 3 times. Okay, it's a little less than 3 times. So by adding the totals, we kind of compared apples to apples a little bit. Because if you notice, there's not the same amount of older people surveyed as younger. Now, if they were 13 and 13, it'd be a little different. It'd be a lot easier when the data's even. When the data's not even, we got to compare. Okay. Now we're going to go one step further. Relative frequencies. These are percentages. And remember, when you take the numerator divided by the denominator times 100 for a percent. Okay? So if you had 1/4, you would take 1 divided by 4, get that decimal, multiply that by 100 to get the percent. Okay? So, if we figured out those percentages, well, we said 9 out of 13 preferred chips, right? 9 out of 13. What percentage would that be? We'll round it to the nearest whole percent for this. 9 divided by 13 times 100. What'd you get? What would you get? Round to the nearest whole percent. 69% is like 692 something, right? Something like that. Yeah. So we'll just round it down. And then the other one is 4 out of 13, which would be doing the same thing, round to the nearest whole percent. 4 out of 13. 31%, like 307, so 31. Notice that when I add these two percentages together, we get 100. Okay? Because again, those two have to equal the whole. Or if there's 3 columns, then they would have to equal the whole, right? All right? So to find the older people, 30 or older, this was 3 divided by 10, because 3 out of 10 people preferred chips of the older people surveyed, right? Well, that's, is 30%, right? Because you get 0.3 times 100. And then the 7 out of 10 surveyed preferred pretzels, which was 70%. So now let's take that same question. Is it 3 times as many people under 30 likely to prefer chips than people over 30? Look at the percentages. Is 69% 3 times more than 30%? No. What percentage is 3 times more than 30%? 90. So this is a little bit more than double, not 3 times. Okay? So as you see, as we kind of dive deeper into it, you can kind of really get the true comparison of what the data represents, than opposed up here just looking at straight numbers. Okay? All right. So let's take this to a different scenario. I'm gonna let you guys kind of practice this a little bit right now. So this is kind of appropriate since we just had an election yesterday, right? So every 4 years, social studies teachers at the middle school hold a mock election. Each student registers as a Democrat, Independent, or Republican, all which are categorical data values. So these guys right here, these are categories, right? Those are categories. This here, this is your numerical data, because they're numbers, right? Make sense? Then the classes hold the primary and final elections for president. So here is the table right here that tells you in the class how many were registered as Democrats, Independents, Republicans that were boys and girls in class. Here's what I want you guys to do. I want you to look at this raw data. Take a few minutes. We're going to figure this out. And use that raw data and come up with true or false for each of these 4 statements. Okay? And then, of course, provide some kind of mathematical proof why you picked true or why you picked false. Okay? So I'm going to pause this. Okay? Keeping it simple. Boys and girls are equally likely to be Democrats. What'd you say here? True. Why? Yeah, 8 and 8 have the same number, right? So true. Okay. That's the raw data. That's what it says, right? Boys are more likely than girls to be independents.
True.
Why?
4 is more than
Yeah, you got 4 boys and 2 girls. So according to this, yeah, 4 is greater than 2. Boys are more likely than girls to be Republicans. Yeah, because you got 12 boys and 6 girls, right? So, pretty easy so far, right? What about girls are only half as likely as boys to be Republicans? Yeah, because 6 is half of 12, right? All right, now, let's add some totals here. Notice how they say there are 24 boys and 16 girls here. So that means if you add across this way, 8 plus 4 plus 12 is 24, and 8 plus 2 plus 6 is 16. That's how they got there, right? So how many total people are in this class?
30.
Total people. 40, right? 24 plus 16 is 40. Okay. Now, in this class, how many total people registered as Democrats? 16. How many people registered as Independent? 6. And then how many people registered as Republicans?
18.
Now again, if you notice, if I add the totals up across the bottom, they should add up to 40, just like these totals. Okay. So now that we added totals, so we can compare apples to apples. Okay. Because again, notice there's not as many girls in the class as boys. So we're not talking about the same thing here. So if we go to here and ask the same question. So girls are equally likely to be, and boys are equally likely to be Democrats. Well, the boys, there were 8 boys, right? Out of how many total boys? 24, right? Can 8 over 24 reduce to a fraction?
Yes.
Simpler fraction. What? 1/3, right? Okay. And now the girls, notice that they were 8 girls that registered Democrat out of 16 total. What does 8/16 reduce to? 8 over 16 is not 2. 1/2. Now, it says equally likely. So are these two fractions the same?
No.
Nope, false. Because 1/3 does not equal 1/2. So now that we're actually comparing apples to apples, notice how one of them just changed. Because remember, on the front, looking at the raw data, they were all true, right? So boys are more likely than girls to be independent. So how many boys were independent? 4 on how many? Not 6. There are 24 boys, right? So 4 out of 24 reduces to what? 1/6. Good. And then the girls, how many girls were independent? 2 out of how many total girls? 16. Does that reduce?
Yeah.
2? 1/8. Now, are these the same fraction? Let me give you a little. I'm gonna give you a little easy way to help compare fractions. Think of cutting a pizza. You got a big round circular pizza. And I cut it into 6 pieces, equal parts. And then I take the same pizza next to it and cut it into 8 equal parts. Which slices are bigger? The 6 part, right? What do you need? The 6 part, right? So 1/6 is bigger than 1/8, right? So is B, is number 2 still true? Is 1/6 bigger than 1/8?
Yeah.
Yes. Now it says boys are more likely than girls to be Republicans. Remember, for the boys, it was 12 out of 24, which reduces to what? A half. And the girls, it was 6 out of how many girls?
16.
Which, what does that reduce to? 6 over 16. Not 2/8. 3/8. So is a half bigger than 3/8?
Yes.
Yeah, because what fraction with the 8 gives us a half? 4/8. So it's a little short, right? So yes, a half is bigger than 3/8. Okay. Now this says girls are only half as likely as boys. Half as likely as boys to be Republicans. So remember, for the boys, we had a half. And for the girls, we had 3/8. Is 3/8 half of a half? Well, remember, if it was half, if I took 3/8 and added to 3/8, what do I get? 6/8, right? 6/8 is bigger than a half, right? Because what's half in eighths? You said 4/8, right? Well, that's bigger than 4/8. So this is false. So if you notice, just by looking at the data for what it actually is, 2 of these changed. And that they're not all true anymore, right? They're not all true. All right, now we kind of did the legwork to find out the percentages down here, right? You notice that we had 8 out of 24, right? And it reduced to 1/3. And when you took 1/3, you got 33 1/3%. You could have wrote it like this too, right? So we try to figure out the percentages for independence. Well, it was 4 out of 24, right, for the boys, and that reduced to 1/6. Anyone tell me what 1/6 is a percent? We'll just go to the nearest 10 since that's what they kind of did here. 1/6. 16 what? 16.7. Is it 6 repeating?
Yeah.
Okay. So 0.6 repeating is 2/3, and 0.3 repeating is 1/3. What happens when I add 2/3 and 1/3 together? 1/3 plus 2/3. 1, right? And then 16 plus 33 is 49, and that 1 gives us 50. So that adds up to 50%. Well, if you look at the Republicans, that was 12 out of 24, which is a half. What's a half as a percentage? 50%. So you notice the whole column or row we added up gives us 100, right? And then for the girls, 8 out of 16 were Democrats. And if you notice, we converted that to a half, right? Which is what percent? 50. And then the girls here the independents was 2 out of 16, which reduced to an eighth. And what does 1/8 as a decimal percent? It's got to be a percent, not a decimal. Just round it to the nearest tenth, like we've been doing the other ones. 12.5. Okay. And then the Republicans were 6 out of 16, which reduced to 3/8. And what is that as a percentage? 3/8. 37.5%. And again, if you add 3 across, that's 100% off. Should always be 100%. All right. Now, using the percentages, I want you to go answer those same questions that we did in Part A. 1, 2, 3, and 4. And see if the percentages change anything. Okay? We'll give you guys a few minutes to do the percentages now. Compare the percentages. So compare them. So are girls equally likely to be Democrats or girls and boys? Look at the percentages. Are those equal?
No.
33 and a third is not the same as 50, right? I think we all agree with that, right? So that's false. Okay. What about the second one? Boys are more likely than girls to be independent. Look at the percentages. She's not here.
Oh, so now.
Boys are more likely than girls to be independent. 16.6% is bigger than 12.5, right? Not by much, but it's still bigger. That doesn't change anything. Okay? So, how about boys are more likely than girls to be Republicans? Yeah, 50 is bigger than 37.5, right? Now, how about girls are only half as likely as boys to be Republicans? Yeah, it's false. Why? Right, half of 50% is what? Is 25%. Right? And 37% more than that, right? So that doesn't work. Right? And that's two-way tables and frequency tables. Not too bad, huh?